Hey, what's up YouTube? In today's video, I'm going to show you how scriptable tools can be used to add cool features to Unreal Engine, like the ability to paint flow maps directly in Engine. As always, on my YouTube channel, this is not a step-by-step tutorial. First, I'll give flow maps a brief introduction and explain some technical aspects to keep in mind when working with them. Next, I'll showcase what my tools can do and how to use them if you're interested in trying them out. Then I'll give Scriptable Tools an introduction and cover the basics. Finally, I'll do a technical breakdown to explain how my tools work in case you want to create something similar yourself. So feel free to use the timestamp below to navigate through the video. Alright, let's get started. Here's a simple test scene with a couple of static meshes. Use your imagination and let's pretend these are rivers, water bodies and so on. Each static mesh uses a material, and each material utilizes a flow map. Flow maps are essentially a more advanced way to scroll a texture. You may have used a texture panner in Unreal Engine, right? Well, a flow map is a technique to give the impression that a texture is scrolled based on a 2D direction stored in a texture called a flow map. A texture is sampled twice, with one sample being offset halfway ahead, and the two samples are interpolated to flip-flop between the two and create a seamless motion. This technique creates the illusion of a texture that quote-unquote moves in the flow direction. Now, it's worth noting that the term flow map can be a bit ambiguous. It can refer to the texture that stores the flow direction, but also to the algorithm I just described. That algorithm, by the way, can be accessed in Unreal Engine using this built-in material function. If you're feeling adventurous, try to make sense of it. You'll see that it does pretty much what I just explained. Let's break it down without all the unnecessary details. We use two texture samplers. UVs are offset by the flow, multiplied by a timer. This timer loops to create a cyclical effect and prevent excessive divergence. The first texture sample has a phase offset, making it half a cycle ahead of the second. We interpolate between the two samples using a linear sine function to hide the jump in UV coordinates when the timer is reset. And that's what's visualized in this debug view, right? The first sample is shown in red, the second sample is shown in blue, and the interpolated sample transitions from red to blue. You'll notice it's fully red when the blue sample resets, and vice versa. This technique creates the impression of a smoothly scrolling texture. Now, obviously, the idea is to control the flow per pixel using a flow map texture rather than using a constant value. Additionally, Unreal Engine adds a 0.5 offset to one of the samplers. This is optional but can enhance the perception of flow and help break up the pattern of a tiling texture. However, it can also cause the texture to sort of blink in place where there's no flow, if that makes sense, something to keep in mind. That's it, that's the algorithm. However, that's not what I'm focusing on today. Today I'm interested in the different ways a flow map texture can be created. Now, I've already shown a couple of techniques in some of my previous videos, but they relied on external software, which can be a bit limiting. That's why I'm attempting to build tools entirely in Engine. But let's first take a minute to explain a few things about flow map textures. A flow map texture is designed to depict the flow's direction and speed at every pixel. Essentially, it's a texture that contains 2D vectors, direction and speed. Two texture channels are enough to store this information. Typically, the red channel stores the flow's X component and the green channel the Y component. This is why flow map textures often appear yellowish. Add red to green in equal proportion and you get yellow. Now let's talk about range and precision. The flow speed is determined by the length of the 2D vector. So a high flow speed means a 2D vector with large X and Y components. And to describe any direction, the X and Y components might need to be negative. However, if you're familiar with 8-bit textures, you know that storing negative values in such texture isn't possible. Plus, with only 8 bits per channel, you have just 256 values to work with, from 0 to 255. or in normalized space from 0 to 1 with 254 steps in between. This means the range is limited and the precision is low. So to encode negative directions in an 8-bit texture, you need to do two things. First, the flow must be contained within a -1 to 1 range. Therefore, you need to set an arbitrary limit for the maximum flow speed to avoid exceeding this range. Next, you need to remap this -1 to 1 range to 0 to 1 using this formula. So in this new mapping, -1 becomes 0, 0 becomes 0.5, and 1 remains 1. And that's why a flow map texture that describes no flow is plain yellow. It simply contains 0.5 in the red and green channels. And when remapped to a -1 to 1 range to reconstruct both positive and negative directions, 0.5 reads as 0 in both x and y, hence no flow. Anyway, that's the math needed to remap the flow between a -1 to 1 range and a 0 to 1 range. You can also use Unreal Engine's constant bias node. It's essentially the same thing. Now, due to this remapping, you can only encode 127 different flow speeds in a given direction, which offers very limited precision. This may cause artifacts and result in a blocky-looking effect. To reduce this issue, you could add noise, as suggested by this node. In fact, it's what it does by default. It adds a bit of spatial noise to the time value used to drive the flow algorithm. Also, with 8-bit textures, the texture compression settings plays a huge role, and flow maps should be set to vector displacement to ensure the data is not compressed. So I kinda lied. The blockiness was a result of compression rather than limited range. But still, that range may actually be a limiting factor and may result in visible artifacts in certain cases. So these are the range and precision considerations you need to keep in mind when working with 8-bit flow map textures. With 16-bit textures, however, things are different. In Unreal Engine, 16-bit textures can store negative numbers and offer much higher precision. This means such texture can encode the flow direction and speed as is without any normalization or remapping. Now, for consistency, I would argue it's best to keep normalizing and remapping the flow, because 16-bit textures use more memory, and you might need to convert 16-bit flow map textures to 8-bit to support lower-end hardware at some point during the production. And you probably don't want to update multiple materials just because you suddenly need to remap values to support 8-bit flow maps. You get my point. That being said, 16-bit flow map textures offer better interpolation due to their higher precision, and often you don't need very fine detail in flow maps. So you can use a lower resolution 16-bit texture instead of a higher resolution 8-bit texture, and thanks to the improved interpolation, achieve better visual quality with a similar, if not lower, memory footprint. You could even use 32-bit textures if you need even more precision, as long as the extra memory cost is worth it. It's up to you. Typically, 16-bit flow maps suffice for most applications, and that's what I'll be using in this video, with the flow normalized and remapped. Also, keep in mind that two channels are currently wasted. The blue and alpha channels are not storing any data, and unlike render targets, which can be configured to only contain two channels, textures are a bit more limited in the format they offer. If you need at least two channels, looks like it's RGBA or nothing. And that's it for the introduction, and now that you're familiar with flow maps, let's see what my tools have to offer. Before we begin, ensure you have the Scriptable Tools plugins enabled. Additionally, I rely on geometry scripting for some features, so make sure that's activated as well. Once you're in the Scriptable Tools editor mode, you'll see a couple of tools under the flow category. Now, painting flow maps on meshes can be complicated. A flow map texture may be mapped either using the mesh UVs, which makes it relative to the surface, or in world space. To accommodate this, there are two paint tools available, one for each mapping method. So it's important to know in advance how your flow map texture is mapped in your material to choose the correct tool. Unfortunately, I couldn't find an elegant way to make one tool that does it all, at least not without creating a bunch of confusing toggles and options, so I instead chose to create two different tools. Anyway, Let's start with the Paint UV tool. You can adjust several settings like the brush radius, strength and fall off. For the other settings, UV channel, material index and texture name, here's what you need to know. The tool performs a line trace to identify a primitive component, such as a static mesh component, under the cursor. Since a mesh can have multiple material slots, you specify which slot to target with the material index. Within that material, the tool searches for a texture sampler parameter or texture object parameter by name, both work. The flow map texture, by the way, can be either a static texture or a render target, both are compatible. And if your flow map texture uses a specific UV channel in the material, specify that with the UV channel setting. With these settings configured, you can paint flow maps directly onto any mesh, as long as materials match the following mapping and parameters criteria. You may hold the Shift key to erase the flow, by the way. Concerning the Paint World tool, well, again, that's if your materials map the flow map textures using the absolute world position rather than with UVs. Thus, you probably specify the mapping location and size in the material, and I assumed that would be done with a single vector4 parameter, so the tool can get that vector4 by name. If it can't, or if you prefer doing things differently, the tool may instead use a custom origin and size. Also, the preview looks a bit different, but nothing to worry about. So, the thing to keep in mind is that using the UV tool to paint flow on this world mapped material wouldn't work. And using the world tool to paint flow on that other UV mapped material wouldn't either. Again, not ideal, and I'm sure there are ways to improve the user experience here, but for now that's how it is. Next, the Clear tool is pretty straightforward. Click on a mesh and it clears the flow texture. Finally, the Resize tool resizes the flow map texture, and that's it, there's not much more to it. Now that we've seen the tools in action, let's take a step back and give Scriptable Tools a brief technical introduction before we dive into the tools blueprints. As of UE 5.3, with the Scriptable Tools plugins enabled, you can create two different types of tools: single click and click and drag. Both types inherit from the interactive tool class, so you could potentially create your own type. But I feel like these two cover most needs. Each type also comes in an editor version that adds extra functions, and as far as I know, these don't come with extra constraints, just more features, so might as well have those, I think. I mean, if you don't need editor-only blueprint nodes, you can opt for a non-editor class, sure. Each tool comes with settings you may want to tweak: tool name, category, and more. You might also want to enable the ability to receive mouse hover events, as I did for all my tools. The editor should, on its own, detect the Scriptable tool blueprints you create and list them in this editor mode. To allow a tool to have settings, you'll need to create a property set blueprint. And I have a gut feeling you need the editor version of that class to work with an editor version of a tool class, if that makes sense. I should double check that information, but I'm lazy. Now, a property set blueprint acts like a variable container, pretty much. And to expose a variable to the user, simply make it instance editable. Next, every Scriptable tool includes an event called onScriptSetup. This event triggers when the script is, I believe, clicked on. And that's when you add the property set to the tool and thus expose the instance editable variables this class contains to the user. It's also considered best practice to cast the return property set to your class and catch the result in a variable to access these tool settings within that blueprint. In addition to the onScriptSetup event, Scriptable Tools comes with a few more events: onScriptTick, onScriptShutdown, triggered when the tool is exited or completed, onScriptRender, called onTick and can be used to draw debug lines in the 3D viewport. Also, you can still draw debug lines on tick, so meh. And to conclude, there's the onScriptDrawHUD event, also called onTick and used to draw debug info on the screen. Similar to onScriptRender, you can sort of do that already, so I'm not sure how necessary that event is, to be honest. There are also gizmo-related events and functions, but I won't cover those in today's video. Feel free to watch my Niagara GPU drips video for more information on that. Now, if the tool is configured to have hover capabilities, you can obviously implement hover events and functions as well. There's a hover begin event triggered when the onHoverHitTest function returns a hit. So you can use the hover pause struct to perform actions like line tracing to see if there's an actor under the cursor and return a hit or a miss. If a hit is returned, the hover begin event is called and a stream of hover update begins. If implemented, this update function should return true to continue the hover unless the hover is no longer relevant, in which case it should return false to trigger the hover end event. The hover end event may also be triggered if a hover has started and the onHoverHitTest function suddenly returns a miss. Also, for click-drag tools, hover testing ceases when a drag begins, so the hover end event may also be called at the start of a click-drag action. So handling hover events can be nuanced, and there are many ways to manage a tool's hover functionality if that's something you even need. You might want to handle everything in the hoverHitTest function, or split your logic between hitTest, hoverBegin, update and end. You get my point, do what makes the most sense to you. And that covers hover events. Regarding click events, there are differences between single-click and click-drag tools, but they start similarly with a test-click function in both cases. For single-click tools, you must override the test if hit by click function to analyze what's under the cursor and see if the tool should consume the click and thus trigger the onHit by click event. On the other hand, click-drag tools have a function called test if can begin click-drag to do the same. Returning a hit triggers the onDrag begin event and starts a stream of onDrag update position events as the drag progresses. Finally, onDrag end is called when the click is released. The drag can also be cancelled for various reasons, such as the cursor leaving the viewport, the window losing focus, and so on. That covers most of the functions and events you can utilize with Scriptable Tools. There are a few aspects I haven't explained, like gizmos and messages, but these are pretty straightforward. Feel free to explore these further on your own. This great article is a must-read, by the way. Now, let's dive deeper and explore some concrete examples. First of all, the ClearFlow and Resize Flow tools utilize the Editor Scriptable Single-Click Tool class, while the two Paint tools use the Editor Scriptable Click-Drag Tool class. Additionally, I've created 4 property set blueprints, one for each tool. Let's start by examining the ClearFlow tool, which is relatively straightforward. During on-script setup, I add the property set as previously explained. Next, in the onHoverHitTest function, I perform a line trace to obtain the hit result under the cursor. This hit result is then passed to a function I called setHoverFromHit, where I retrieve the hit component, store it in a local variable, and check its validity. There might not be a primitive under the cursor after all. If the primitive component is valid, I proceed to fetch its material at the specified index, that user-exposed setting. If this material happens to be a material instance dynamic, then great, I cache it in a local variable. If not, well shoot, I need to create one because I need access to the flow texture asset used by this material. Unfortunately, a simple material interface doesn't let you do that. It must be a material instance dynamic. However, since this is a ticking process, I certainly want to avoid creating a new material instance every tick. Thus, I've implemented a caching system. First, I check if the primitive component I hovered over last tick is the same as the current one. If so, I verify if its material interface matches the one I last cached. And if it's indeed the same material, I then check if I have already cached a dynamic instance of it. If so, I retrieve it. Otherwise, I create a new one. With this dynamic instance, I can access the flow texture used by either a texture sampler or a texture object with a specified parameter name. Now, that texture object could be many things. If it's a texture 2D, I cache it in a local variable. Else, if it's a render target 2D, I cache that one instead. At this stage, I consider the hover context to be valid. With that hover context now cached in local variables, I proceed by comparing this context with the one from the previous tick. If the current hover context is invalid, well, I no longer need to display any preview for the hovered primitive, so I hide the preview actor. More details on this shortly. Next, I clear the reference to the hovered primitive. However, if the hover context is valid, well, first I compare the current hovered primitive with the one from the previous tick. If they differ and are both valid, I need to update the preview accordingly. Finally, these local variables from this current hover context are stored in global variables. This allows me to compare them next tick and potentially reuse a previously created material instance dynamic if applicable, otherwise it will be garbage collected. That's essentially what prevents me from having to create a new one per tick, and also helps me detect any changes in the hovered primitive and create an event-driven system. The preview is updated only when necessary. So at this point, the only remaining unknown is this bit here. What is this preview thing anyway? Well, it allows me to draw a wireframe and highlight the hovered mesh. And to avoid altering the original primitive and potentially causing issues due to unforeseen programming errors, I chose instead to create an actor that mirrors the hovered mesh. This approach lets me manipulate the copy without risk to the source primitive, if that makes sense. So this macro facilitates fetching or creating this preview actor as needed. Once retrieved, I invoke its configure preview function to specify which primitive to copy and set up the preview. Now, to understand what happens next, it's crucial to know this actor isn't just any actor. It's a generated dynamic mesh actor. You see, when hovering a static mesh component, I could simply fetch its static mesh and create extra static mesh components to duplicate it. But if the primitive isn't a static mesh component, for example if it's a dynamic mesh, that straightforward approach wouldn't work. Hence the reliance on geometry scripting, which is a plugin requirement for my tools. However, geometry scripting isn't just for previews, as you'll soon see. Now, while I won't dive deep into geometry scripting here, as this video isn't focused on that, the function itself isn't overly complex, so let's break it down real quick. Essentially, I pass the primitive to geometry scripting's copy mesh from component function. This function attempts to replicate any mesh information stored within the primitive. Once copied, I assign the wireframe material to that mesh. Then I duplicate the mesh, assign a new material ID to apply the highlight material. And that's essentially how the preview is set up. This approach enables the tool to both display a wireframe of the hovered mesh and highlight it. And when the cursor is no longer hovering over anything, the preview actor is simply hidden. Additionally, when the tool shuts down, the preview actor is destroyed. And that summarizes the preview mechanism when hovering over a mesh. And the other tools utilize the same technique. The final piece of the puzzle is what happens when I click. Again, it starts with a test if hit by click function. I simply reuse the hit structure cached in the onHover hit test function. Since I'm clicking where the cursor hovers, I don't think it's necessary to line trace again, unless there's a 1 frame delay between hover and click events that I'm not aware of, and ensuring you have the latest information is crucial. But I have not encountered any issues with this approach. Anyway, if I hover over a valid primitive component, I consume the click. I then utilize the information gathered during the hover. If I'm hovering and found a render target from the trace, I simply clear that render target. If the line trace found a texture 2D instead, I handle it differently. I create a render target with a matching size and format, specifying a clear color. Again, working with normalized and remapped flow maps means no flow equates to 0.5 in both X and Y, meaning the red and green channels. Then I convert that render target into a static texture to replace the existing texture with it. By the way, render targets offer two functions for converting them into texture assets. One overwrites the specified texture, while the other always creates a new texture asset. Now, one thing to keep in mind is that a texture may come in many different formats, some definitely not suited for flow maps, like say 16 bits red channel only, right? To me, only 3 make sense: uncompressed 8 bits, uncompressed 16 bits, and 32 bits. However, I do not ensure the texture found has one of these three formats. Something I could do, but whatever. I didn't want to create arbitrary constraints on what texture formats are suitable for flow maps based on my own opinion. You may disagree and consider compressed 8-bit textures do the job well enough for your own use case. My point is, the tool can encounter many different contexts, different texture compression settings, different ways a flow map texture can be mapped in a material, multiple material slots, different primitive components, like say an instance static mesh component, a procedural mesh component, a landscape, and so on. And so I can't guarantee these tools are going to work for your use case. At one point, I wasn't even sure I could keep the texture compression settings. You see, this function has the tendency to reset the texture format to default, especially when converting 8-bit render targets, it seems. And so my fix was, before calling this function, cache these textures compression settings so I could ensure it's still the same after replacing the asset with a render target. That, however, had the tendency to crash Unreal Engine, due to something having to do with asynchronous processes not completed and whatnot. Thankfully, Ryan came to the rescue and suggested enabling defer compression to fix this, and it worked. So big thanks for the help. Feel free to check out its Get Relief plugin to generate relaxed cone step maps. Awesome stuff. Anyway, the tool can then automatically be shut down if needed, and that wraps up the clear tool. That's how it operates. Clicking on a primitive triggers the tool to locate and clear the flow map texture used in the primitive's material by using a render target to override the existing texture. The Resize tool operates similarly to the clear tool, with a key distinction. If the material uses a render target, I don't clear it anymore, but I resize it to match the specified dimensions. And for materials using a texture, I still create a corresponding render target. I next create a dynamic material instance of a material that uses a single texture parameter named texture. And so I set that material's texture to be the one I want to resize, draw the material into the render target, and then overwrite the original texture with the resized render target. And that resizes the texture. Now, side note, when writing a material to a render target, managing the alpha channel can be tricky. My preferred setup involves using an unlit masked material with a clip mask set to 0, allowing negative emissive color, and enabling used with editor compositing to achieve a more predictable alpha channel behavior. It's still not without flaws, and Niagara is a much stronger alternative to manipulate render targets, but it sadly involves a lot more work to set up. Anyway, that's pretty much it for the Resize tool. And let's quickly demonstrate it. Say I want to use a 512 resolution, click on the mesh, verify the texture size is 512, and yep. Now resize it to 128, and it works. Now onto the paint tool. This is obviously the most intricate one, so buckle up. Unlike the clear and resize tools, the paint tool is based on the click-drag tool class, exposing drag events as explained earlier. Setting properties remains similar, but now I monitor changes to 3 settings to trigger a function called reset paint context. This function closes the paint context and resets associated variables. More on that in a minute. The hover functionality is mostly the same, with minor adjustments to display the brush radius and fall off on the highlighted mesh via a material instance dynamic and sphere masks, nothing too fancy. Let's focus on the painting process itself. When clicking, I reuse the hover line trace to determine if the click should be processed. If so, the onDrag begin event is triggered and calls a function I called startPaint. Similar to how I cache the hover context in global variables, I now store a paint context as well. I verify if the primitive I'm painting on is valid and differs from the one painted last, with the previous brush stroke. If so, it indicates a change in the paint context, necessitating further actions. First, I verify if the texture obtained is the same as the last known one. Even if I clicked on a new primitive that uses a different material, that material could use the same flow texture, allowing me to skip certain steps if that's the case. If a new primitive is detected, indicating a new paint context, I close the current context. Diving into this function isn't going to make too much sense if you don't know what starting a context first means. I start a new paint context by copying over the hover context. If I'm working with a new texture asset, I first copy it into a render target using a method similar to what was demonstrated in the Resize tool. Subsequently, I replace the primitive's material with a dynamic material instance created earlier, and I update it to ensure that it no longer uses its original flow map static texture, but the render target instead, allowing visualization of the flow as it is painted and updated. Finally, the dynamic material instance, responsible for drawing the flow, is updated to reference the render target as its texture. More on that later on. So basically, upon starting a new paint context, I replace a few things. As a result, closing a paint context means restoring these things. And this involves replacing the texture with the painted on render target, and potentially releasing it. Additionally, I restore the primitive's material, and if that was a dynamic material instance to begin with, I restore its texture asset. Alright, let's take a moment to summarize. In the hover test function, I line trace under the cursor to get a primitive on its material and construct a quote-unquote hover context. Upon click, those references are used to create what I called a paint context. A dynamic instance of that material is also created during the hover event, if needed, to access the flow map texture it uses. Those resources are also passed along upon click when starting a paint context. The texture retrieved from the material instance dynamic is then copied into a render target that is modified as I paint onto the mesh. Starting a paint context also means replacing this primitive's material with the dynamic instance I created, which is configured to use the render target instead of the original flow map texture. And you can somewhat see this process in action. This static mesh component uses a basic material that is switched to a dynamic instance when the painting starts. And that dynamic instance overrides the flow texture parameter to point to a render target. Then painting onto another primitive resets this primitive's material because of this branch being true for one single frame, and the closure of the current paint context. The flow map texture is overwritten with a render target that is, at first, just a one-to-one copy of the original flow map texture. And we are halfway there. The only remaining step is to understand how the flow is painted into the render target as the cursor moves. Sadly, that's not that easy. Well, it's not that bad, but there are lots of technical details that complicate things and many angles of approach to solve this problem. Let's dive into it. Painting happens during the drag update and drag end events. First, I simply make sure the cursor is still over the same primitive we started painting on, and that all references are valid. Next, I need to determine the brush's position in UV space. This is where it gets tricky, but more on that shortly. This macro helps me get or create a dynamic instance of the paint material that is configured and drawn into the render target. The material parameters include the brush's UV location, the flow's X and Y components, and the brush's radius, which is used to create a sphere mask to apply the flow to the render target. Holding the Shift key erases flow by interpolating the render target back to the neutral flow value, meaning 0.5 in both X and Y. And blue and alpha channels are unaffected. That's the gist of it. The main challenge is accurately translating the brush position, size and direction into UV space. Side note, this tool, as I said, operates in UV space, which has its advantages and drawbacks. Alternatively, you could work in world space, which also has its own set of pros and cons. Having the brush location in 3D space, you could simply compute its movement based on the brush's previous position. Convert that vector from world to tangent space, relative to the surface, and mask it based on the brush's radius in centimeters using a 3D sphere mask, and that be the flow to draw into the render target. The thing is, that's not so easily done. Keep in mind I'm simply drawing a material into a render target, so that material has no knowledge of any mesh whatsoever. Its absolute world position node doesn't output the reconstructed world position of a pixel on a 3D surface, and it has no matrix to transform from world to tangent space. Now, you could bring that information to the material. You could bake the mesh's world position surface data into a texture, allowing the material thrown into the render target to sample it, and ultimately recreating the absolute world position node. Geometry scripting or the modeling mode can bake such texture, by the way. I think you'd also need to bake the mesh normals and tangents in textures to perform the world to tangent space transformation manually. Setting this up can be tedious and could also be problematic around UV borders. You might need to float these maps using techniques like the jump float algorithm, and that would further complicate things. Despite the setup effort, using world space has significant advantages when painting on a mesh. The brush radius in centimeters can be used as is to create the brush mask, and the brush can paint seamlessly across UV seams without worrying about UV continuity or stretch. Great benefits. Now, instead of baking textures to provide mesh data to the material rendered into the render target, you could just not render a material into a render target and use a scene capture component instead. Painting could thus be done in world space using the mesh's material. The mesh could then be unwrapped in the vertex shader to be rendered in the render target using an additive process. But that again can be a bit tedious to set up, and rasterization may still cause troubles around UV borders. Feel free to watch that very old video of mine where I showcased how I painted localized damage on skeletal meshes using this technique. Niagara is also a great alternative to do something alike. There are techniques that let you bypass a scene capture component and compute effects in world space, something I'm experimenting with a bit lately. I'll probably do a video on this at some point. Ultimately, there are many ways to quote-unquote paint a mesh. I chose to keep it somewhat simple and do things with a draw material into render target node and work in UV space because, well, gotta choose a technique. And while pondering if it was worth making geometry scripting a requirement for this tool just to create the hover effect, I realized I could use geometry scripting to easily convert the brush location from world to UV space, so I went with it. Now, enabling a project settings can allow each results to return UV positions directly, so you could technically bypass geometry scripting. But I have a gut feeling this option affects performance globally in one way or another. But I could be wrong. In doubt, I preferred to not make this a requirement and rely on geometry scripting instead. So I copy the mesh and build a BVH tree to find where the cursor's world space location is closest to on the mesh. This gives me a triangle ID and barycentric coordinates, which let me interpolate and determine the brush's UV position. It's then compared to the last UV position I cached to determine the flow to paint in UV space. That is sent to the material, and voila, the painting is applied. Well, almost. You may have noticed there's a bit more to this function. Yeah, there's still one last problem I haven't mentioned. That is, converting the brush radius from world to UV space. No, it may not even be a problem. I could simply assume the brush radius is in UV space to begin with. That, however, wouldn't translate to a very pleasing user experience. See, these two planes share the same UV but have a different scale, resulting in a 0 to 1 UV area that doesn't correlate to the same area in world space. Thus, a brush radius of say 0.1 would result in dramatically different sizes, not great. Thus, I feel like it's best to keep this value in centimeters, so the user has something consistent to work with and knows what to expect. But to come up with a world to UV scale conversion that is consistent across all surfaces and all UV layouts is complicated, but I could be missing something. What I ended up doing is some kind of hack inspired by DDX and DDY derivatives. In that function, I not only interpolate and compute the UV position, but also the mesh tangent and bitangent. And this allows me to take a step forward, but also to the right on the surface, and compute two more UV positions to create a mapping between a distance in world space and a distance in UV space, and thus create some kind of scale factor per triangle. And that somewhat works. It's not perfect, but it's the best I could come up with. Now I have to point out one major flaw when painting in UV space. UV continuity. See that mesh? It's connected, but UVs are split. So when painting on that mesh, the tool tracks the brush delta position in UV space to compute the flow to paint, right? Thus, the tool may register a huge brush movement when crossing UV seams, because the brush may be suddenly teleported in UV space. So that's an issue, one I'm not sure how to fix. I also want to mention another issue, or I'd rather say limitation. It has nothing to do with UV space and whatnot, but it's still something to know. See, these two static mesh components use a different material. But each material samples the same flow map texture, and it's fine. But when painting on a mesh, that mesh and that mesh only sees the flow map being updated in real time, the other not. That's because of that material swapping mechanism, right? And so when painting on that other mesh, you may suddenly get to see an abrupt change in the flow, because only then you may see the updated flow map texture applied on that mesh. Again, not a bug, but a limitation. And I'm not sure how to fix it, but I don't think it's a huge issue. Anyway, that's the end of it. That's how I can paint flow maps on different primitives and materials in Editor. Hopefully I made enough sense to put you on the right track in case you want to build something like this. Files are also available as a tier 2 reward on my Patreon, along with many great educational UE projects, systems, demos and assets. Thanks by the way to all my Patreon supporters for the incredible support, and thanks to you all for watching. Consider leaving a like and subscribing to the channel if you liked the video. Alright, I'll see you in the next video, take care of yourself, bye bye!